Your childhood photo reveals how much you have changed, but the cosmos is transforming on a scale you can hardly believe. We often picture the universe as a still and silent painting, yet it is a living, breathing entity in constant motion. This journey uncovers 20 unexpected ways the universe changes over time, and we can actually see it happening. You will discover a cosmos where galaxies collide, stars are born and die, and the very fabric of space stretches, all observable through our telescopes. How did the faint afterglow of creation cool to almost absolute zero? What force is pushing the cosmos to expand faster and faster? By the end, you will see the night sky not as a static picture, but as a single frame in an epic movie of cosmic evolution. What part of this endless transformation captures your imagination the most? The cosmos is not just growing, it is running away from itself. Think of a loaf of raisin bread baking in an oven, where each raisin is a galaxy. As the dough expands, every raisin moves away from every other one. This is the classic picture of our expanding universe, but the real story is far more strange. Observations of distant, exploding stars revealed something that stunned astronomers. The expansion is not slowing down, as everyone expected. It is speeding up. The universe is stretching faster and faster over time, driven by a mysterious and invisible force we call dark energy. This discovery was so monumental it earned a Nobel Prize. We can actually see this acceleration by studying the light from far-off galaxies. As they rush away, their light is stretched, shifting its color towards the red end of the spectrum. This redshift is a direct measurement of their flight. What does this relentless acceleration mean for the future? It paints a picture of a cosmos where, one day, distant galaxies will have receded so far that their light can no longer reach us. Our observable universe will become a much smaller and lonelier island in the void. This grand, accelerating flight forces us to confront the fate of the very stars that light up the darkness. That fading ember from the beginning of everything has a name: the cosmic microwave background. It is the oldest light in the universe, a ghostly whisper that has been traveling for over 13 billion years. Think of it as the residual heat from the Big Bang itself, a brilliant fireball that has cooled to a faint, uniform glow bathing the entire cosmos. When this light first burst forth, the universe was a searing hot plasma. Today, its temperature has plummeted to just a few degrees above absolute zero. We can measure this incredible cool down with stunning precision. Satellites like Planck have mapped this background radiation in exquisite detail, revealing a tapestry of tiny temperature fluctuations. These minute variations, these hot and cold spots, are not random. They are the cosmic seeds, the imprints of gravity that would one day pull matter together into the first galaxies and stars. This continuous dimming is a direct result of the universe stretching. As space expands, it stretches the very wavelengths of this ancient light, shifting its energy from visible heat into the microwave part of the spectrum. This is not a theoretical idea, it is a change we can observe and measure. It is the universe's permanent cooling record, a direct line back to its fiery birth. And that faint, cooling echo set the stage for a dramatic new chapter, the moment the cosmic dark ages ended and the first brilliant objects ignited. The darkness did not last forever. That ancient cosmic glow was the prelude to the first great light shows, the birth of the very first stars. This leads us to the third great transformation, the continuous cycle of stellar birth and death within vast clouds of gas and dust known as nebulae. Look at the Orion Nebula, a stellar nursery visible to the naked eye. It is not a static painting of light, but a dynamic, churning factory where new stars are constantly being forged. Within these colossal clouds, gravity works its magic, pulling together pockets of hydrogen and helium until they collapse under their own weight. The pressure and heat at the core become so immense that nuclear fusion ignites and a new star blazes to life. We can witness this directly. Telescopes like Hubble and the James Webb Space Telescope show us protostars, these infant suns still swaddled in their dusty cocoons, and capture violent jets of material screaming away from their poles. But for every birth, there is a death. Massive stars, living fast and dying young, end their lives in cataclysmic explosions known as supernovae. The Crab Nebula is the expanding, tangled wreckage of such an event, a star that Chinese astronomers saw explode nearly 1,000 years ago. That cloud is still rushing outward, a testament to a violent change we can watch in real time. This cycle is the universe's great recycling program. A supernova does not just destroy, it creates. The incredible forces in that explosion forge heavy elements like iron, gold, and uranium, scattering them across the galaxy. The iron in your blood and the gold in a wedding ring were all forged in the heart of a dying star long ago. This process changes a galaxy's very identity. The rate of star formation can surge in a burst of frantic activity, lighting up a galaxy with brilliant blue young stars, or it can slow to a quiet trickle, leaving it dominated by older, redder suns. This life cycle, this endless dance of creation and destruction, is what builds galaxies over billions of years, and all that scattered material, that cosmic dust and gas enriched with new elements, eventually collapses again under gravity's pull. What new structures does this recycled stardust build when it gathers on a scale far larger than any single star? That recycled stardust does not just form new stars, it builds entire galaxies, and these colossal cities of stars are themselves locked in a slow, gravitational dance. Two vast islands of stars, each home to billions of suns, can drift together over billions of years until they gravitationally embrace. They do not collide in a fiery crash, for the distances between stars are immense. Instead, they begin a long and intricate merger, swirling together to form a new, larger galaxy. We can see this cosmic metamorphosis happening right now. Look at the antennae galaxies, a pair of spirals caught in a violent embrace. Their long, streaming tails of stars, flung out by immense tidal forces, give them their name. Within those tangled regions, clouds of gas are being violently compressed, triggering firestorms of new star birth, lighting up the collision with brilliant blue clusters of young stars. These mergers completely reshape a galaxy's identity. The graceful, orderly spiral arms are stretched and twisted beyond recognition. Over time, through multiple mergers, a galaxy's very morphology can change, transforming from a structured spiral into a smooth, featureless elliptical galaxy. This process is a key mechanism for galactic growth, showing that galaxies are not isolated islands. They are socially interactive, their fates intertwined by gravity. And at the heart of this chaos, something else is stirred awake. The same gravitational forces that funnel gas into the galactic core also feed the supermassive black holes lurking there. What happens when these sleeping giants are suddenly presented with a vast feast of cosmic material? That dormant giant, once awakened, becomes the most powerful engine in the cosmos. A supermassive black hole, after a feast of gas and stars, can transform into a brilliant quasar, an active galactic nucleus so luminous it can outshine every single star in its host galaxy combined. This is not a gentle flicker to life, it is a violent awakening. we see this dramatic change across the universe, from galaxies with quiet, sleeping black holes to those blazing with the light of an active core. The difference is simply a matter of fuel. When a galaxy merger or a dense cloud of gas spirals into the center, the black hole has a meal. As this material is pulled inward, it forms a searingly hot, swirling disk of plasma, and the immense friction and magnetic forces can launch jets of particles traveling at nearly the speed of light. This entire chaotic system is what we observe as an active galaxy, and by looking deep into space and therefore back in time, we have learned that the universe was once a much brighter, more violent place. Quasars were far more common billions of years ago, a testament to a more crowded, gas-rich cosmic environment. Their activity is not constant. It flickers and fades as the fuel supply runs out, leaving behind a dormant black hole once more. But in their active phase, these monsters do not just create light, they wield immense power over their entire galaxy. The energy they release drives colossal winds and shockwaves that blast through interstellar space. This process, known as quenching, heats up the vast reservoirs of cold gas needed to form new stars, effectively shutting down star birth. It is a dramatic form of cosmic feedback. The black hole, by feasting, eventually terminates the very conditions that allowed it to awaken. This reveals a profound truth that these gravitational behemoths are not just destructive voids. They are key architects regulating the growth and ultimately determining the final structure of their host galaxies. The energy from these outbursts does not simply vanish. It travels far beyond a single galaxy, pouring into the vast, empty spaces between galaxies, where it contributes to the next great transformation of our universe. That vast energy pouring from quasars and supernovae does not simply vanish into the emptiness. It floods into the thin, invisible gas that weaves between the galaxies, a cosmic ocean known as the intergalactic medium. For a long time, we might have pictured this space as a cold, dark void, but it is far from inert. It is continuously being heated and enriched by these titanic outbursts. The colossal winds from exploding stars and the relativistic jets screaming from active black holes act like cosmic blowtorches, pumping immense energy into this diffuse web. This energy raises the temperature of the gas and violently strips electrons from the hydrogen atoms that float within it, a process called ionization. We can actually detect this transformation. When astronomers study the light from the most distant quasars, they see a unique fingerprint in its spectrum, a forest of dark absorption lines. Each line is a snapshot, a record of the ionization state of this intergalactic gas at a specific moment in cosmic history. This heating process has a profound consequence for the entire universe. It effectively puts a brake on the formation of new galaxies. In the early cosmos, this intergalactic gas was colder and denser, allowing it to collapse easily under gravity's pull to build the first structures. But as the medium grew hotter and more ionized over billions of years, that same gas became more energetic and resistant to collapse. It became harder for gravity to gather the material needed to form new galaxies, slowing down the pace of cosmic construction. This is a critical feedback loop, a self-regulating mechanism where the very act of star formation and black hole activity changes the environment to limit future growth. The universe, in its later years, became a less hospitable place for building new galactic cities, and this heated, ionized medium does more than just influence galaxy formation. It also changes the very nature of space itself. How does this cosmic fog affect the light that has to travel through it for billions of years to reach our eyes? That cosmic fog, once heated and ionized, completely transformed the universe's ability to be seen. For hundreds of millions of years after the Big Bang, the cosmos was shrouded in a thick, primordial haze. Neutral hydrogen gas, the most common substance in existence, filled all of space, and it was utterly opaque to the energetic ultraviolet light pouring from the first stars and galaxies. Imagine being inside a dense, impenetrable fog where brilliant headlights can only illuminate a few feet ahead. The light from those first celestial objects was trapped, absorbed almost immediately by the surrounding gas, unable to travel far. Then a great clearing began. This was the Epoch of Re-ionization, a profound cosmic metamorphosis. The intense ultraviolet radiation from those first stars and early quasars acted like a universal sunrise, slowly but surely burning away the fog. It ripped electrons from the hydrogen atoms, changing them from neutral to ionized, and in doing so, it made the universe transparent to that very same light. This was not an instantaneous flip of a switch, but a gradual process that unfolded over several 100 million years as bubbles of clear, ionized space grew and merged until they filled the entire cosmos. We can actually observe evidence of this great transition when astronomers point their most powerful telescopes at the light from quasars billions of light years away. They see a telltale signature in their spectra, a forest of dark lines known as the Lyman Alpha Forest. Each line is a snapshot of a remaining pocket of that primordial hydrogen fog, being progressively eroded by the advancing light of the early universe. This change in transparency was a fundamental phase shift for all of reality. It meant that light, which had been a local phenomenon, could now become a cosmic traveler. Photons could finally race across the vast emptiness of space for billions of years without being absorbed, carrying their stories directly to our telescopes. Without this great clearing, the universe would remain a murky, invisible realm to us. We would be blind to its deepest history. This reionization allowed the intricate cosmic web of galaxies to become visible, painting the detailed picture of the universe we observe today. Yet, even as these grand structures came into view, they were already beginning a slow and relentless process of their own decay. Even the largest structures in the cosmos are not immune to decay. Galaxy clusters, the immense metropolises of the universe containing thousands of galaxies, appear permanent from our fleeting perspective, yet they are locked in a slow, cosmic tug of war. Their immense gravity constantly pulls in new galaxies and smaller groups, building their mass over eons, but another, more relentless force is working against them, the accelerating expansion driven by dark energy. For now, gravity holds these colossal structures together, but over trillions of years, dark energy will win. It will stretch the very fabric of space between the member galaxies until their gravitational bonds are broken, causing these great clusters to slowly drift apart and dissolve into the expanding void. This is not just a future prediction. We can see the dynamics at play today. The motions of galaxies within clusters and the subtle distortions of background light, a phenomenon called gravitational lensing, reveal the invisible scaffolding of dark matter that holds everything together. These dark matter halos are not static sculptures either. Supercomputer simulations show them as dynamic entities, constantly evolving as they merge with other halos and accrete more material, their shapes and densities shifting over cosmic time. The gradual erosion of these largest structures is a direct consequence of the universe's accelerating expansion, a testament to the ultimate dominance of dark energy over even the most powerful gravitational pulls. And as these titanic clusters slowly unravel, their dissolution echoes down to affect the motion of objects much closer to home, even within our own solar system. Even the clockwork precision of our solar system is an illusion of our brief human timescale. The planets are engaged in a slow, gravitational dance that subtly reshapes their paths over millions of years. This process, called secular evolution, means a planet's orbit is not a fixed ellipse but a living, breathing path that slowly oscillates in its shape and tilt. The gentle, persistent tugs between worlds, especially from the giants Jupiter and Saturn, act like a cosmic metronome, setting rhythms that take hundreds of thousands of years to complete. For Mars, this rhythm means its currently slightly elongated orbit is predicted to become more circular in the distant future. Earth's own path around the Sun may also shift, becoming a bit more elliptical, which would slightly alter the intensity of our seasons over these grand cycles. We are not just guessing at this, we can see this migration in action around other stars. Astronomers have found gas giants called hot Jupiters orbiting breathtakingly close to their suns. These planets could not have formed in such infernal locations. They must have been born farther out and then spiraled inward over eons, their orbits dramatically changed by gravitational interactions with other planets or with a disk of primordial gas. This reveals a profound truth that no planetary system is born with its final architecture. The layout is a temporary arrangement, constantly evolving. These gradual orbital changes can have staggering consequences for the possibility of life. A world orbiting comfortably in a star's habitable zone could, over millions of years, be nudged into a more eccentric path, sending it swinging between scorching heat and deep freeze, potentially ending any chance for a stable biosphere. The dance of the orbits is a silent, slow force that writes the long-term destiny of worlds, and as these paths slowly shift, the planets themselves are undergoing dramatic physical transformations. The surfaces of worlds are not timeless monuments, but living diaries constantly being rewritten. Our own planet Earth is a perfect example, its familiar continents adrift on a churning mantle, with volcanoes and earthquakes continuously sculpting new mountains and ocean floors. But for a truly dramatic display, look to Jupiter's moon Io. This tortured world is the most volcanically active place we know, its surface completely repaved by furious eruptions every few million years. We do not have to imagine this transformation, we have watched it happen. Spacecraft like Galileo and Juno have captured stunning images of Io's volcanoes in the very act of blasting plumes hundreds of miles high, painting its surface in vivid shades of sulfur and silicate rock. This is change on a planetary scale, visible in real time. The same is true at Saturn's icy moon Enceladus, where the Cassini spacecraft flew through towering geysers of freshwater ice erupting from a global ocean, a clear sign that its frozen crust is actively renewing itself. Even Venus, shrouded in thick clouds, has had its volcanic past revealed by radar maps showing vast, fresh lava flows suggesting it may still be geologically alive today. This activity is the direct result of a world's internal fire. For Io, the heat comes from the relentless gravitational squeezing by Jupiter, keeping its interior molten. For Earth, it is a combination of leftover heat from its formation and the decay of radioactive elements deep within. But this heat is a finite resource, slowly diminishing over billions of years. A planet's capacity for change itself changes, its internal engine gradually winding down. A world like Mars, now a frigid desert, shows extensive evidence of a warmer, wetter past, with river valleys and lake beds etched into its surface, proving its face was once as dynamic as Earth's. This relentless resurfacing is a cosmic form of editing, erasing ancient crater scars and past environments to write a new geological chapter. It is a process that simultaneously destroys the old history of a world while meticulously recording a new one in layers of lava and sediment. And as these new surfaces are laid down, they immediately begin a slower, more subtle transformation under the relentless assault from the space environment itself. That relentless resurfacing is immediately met by an equally powerful force of erosion. The surface of our own moon, a silent gray world in our sky, is far from a static monument. It is being continuously sandblasted by the harsh environment of space. Without an atmosphere to act as a protective shield, the lunar surface is directly exposed to a relentless rain of micrometeorites, tiny particles of space dust that strike at incredible speeds. This constant bombardment acts like a cosmic mortar and pestle, slowly grinding the bedrock into a fine, powdery soil called regolith. At the same time, the solar wind, a stream of charged particles constantly flowing from the sun, bombards the surface and becomes implanted in the soil grains, subtly altering their chemical makeup. We can actually see the effects of this space weathering with our own eyes or through a simple telescope. Compare the brilliant, bright rays surrounding a fresh crater like Tycho to the darker, more subdued plains of the lunar Maria. The Maria are older, and their surfaces have been exposed to this cosmic weathering for much longer, causing them to darken and even take on a slightly reddish tint. This is not unique to the Moon. Every airless body, from the asteroid Vesta to the sun-scorched planet Mercury, undergoes this same process. It fundamentally changes how these worlds reflect light, which is a critical tool for astronomers trying to determine their composition from vast distances. The surface we observe today is not the pristine surface from its formation. It is a weathered skin, a detailed diary of its exposure history to the violent frontier of space. And as this slow-motion sandblasting alters their faces, the orbits of these small worlds are also far from stable, pulled by gravitational tides in a dance that can fling them across the solar system. Even a small, spinning asteroid is a world of subtle forces. Sunlight warms its surface, but this heating is not uniform. The side facing the sun soaks up energy and becomes hot, while the night side radiates its heat away into the cold vacuum. This simple daily cycle creates an extraordinary push. As the hot surface rotates into darkness, it re-radiates that stored thermal energy, acting like a tiny, gentle rocket thruster. This is the Yarkovsky Effect, a whisper of a force that, over millions of years, can steer an asteroid onto an entirely new path through the solar system. We are not just theorizing about this. By tracking near-Earth asteroids with incredible precision, astronomers have detected minuscule shifts in their orbits that gravity alone cannot explain. These discrepancies are the direct fingerprint of this thermal recoil, a continuous nudge that builds up over eons. This effect is a primary delivery mechanism for meteorites. It can slowly push rocks from the safe confines of the asteroid belt into orbits that eventually cross our own, bringing the raw materials of the early solar system and sometimes danger to our doorstep. For scientists trying to predict the long-term future of asteroid trajectories, the Yarkovsky effect introduces a complex variable. It means we cannot simply calculate an asteroid's path based on gravity alone. We must also account for its rotation, its size, and even the texture of its surface, as a dark, dusty rock will absorb heat differently than a bright, metallic one. This reveals that the orbits of the smallest worlds are living histories, shaped not just by the grand pull of the sun, but by the quiet, persistent physics of light and heat. As these rocky bodies are gently nudged through the void, the stage upon which they move, the very geometry of space, is also undergoing a profound and continuous transformation. The quiet nudge of an asteroid's orbit is governed by the gentle push of sunlight, but the forces at work deep inside worlds are anything but gentle. A planet's magnetic field is a roaring, invisible shield, and Earth's own is far from a steady hum. It is a living, breathing entity that fluctuates in strength and most dramatically flips its entire polarity every few 100,000 years. We can read the history of these reversals like chapters in a stone book. When volcanic rock cools, tiny magnetic minerals within it freeze in place, aligned with the planet's magnetic field at that exact moment. By studying these ancient rocks, we see a record of a magnetic field that has swapped north and south again and again throughout Earth's history. This dynamism is not unique to our world. Our Sun operates on an 11-year heartbeat, a magnetic cycle where its field becomes increasingly tangled, manifesting as dark sunspots and violent solar flares before it completely reverses polarity. We observe this same process on other stars, watching their brightness flicker as massive starspots, many times larger than those on our Sun, rotate in and out of view. Some stars exhibit magnetic activity so violent it unleashes stellar flares that would sterilize any nearby planet, a constant reminder that a star's magnetic personality is a key factor in the habitability of its system. The engine for all this magnetic drama lies deep within, in the churning motions of electrically conductive fluids. On Earth, it is the liquid iron outer core. In the Sun, it is the searing plasma. This internal dynamo, powered by heat and rotation, is what generates the field, but like any engine, it can run down. As a planet cools internally and its rotation gradually slows, the dynamo can weaken and ultimately fail. We see this starkly on Mars. Evidence from orbiters shows that the red planet once had a global magnetic field, but its smaller size allowed its core to cool, its dynamo to cease, and its protective shield to vanish. This loss was catastrophic. Without that magnetic bubble, the solar wind stripped away most of its atmosphere, transforming a potentially habitable world into the frozen desert we see today. The rise and fall of a magnetic field is one of the most fundamental transformations a world can undergo, a silent protector whose presence or absence writes the ultimate fate of an entire planet. And when these magnetic fields are stretched and twisted to their breaking point, they can unleash the most concentrated form of energy in the entire universe. The fading of a gamma-ray burst's afterglow is a cosmic spectacle of violent creation and dissolution. These titanic explosions are the most powerful blasts since the universe began, capable of unleashing more energy in 10 seconds than our Sun will emit across its entire 10 billion-year life. The initial flash of gamma rays is blindingly brief, a pulse of pure power signaling a stellar catastrophe. But the story does not end there. That initial flash is followed by a lingering multi-wavelength afterglow, a fading echo that can be tracked for days or weeks. This afterglow is born from the expanding shockwave of the explosion as it plows into the surrounding interstellar material, heating it to incredible temperatures and causing it to glow across the electromagnetic spectrum, from X-rays to visible light and radio waves. We can actually watch this cosmic fire die down in real time. When satellites detect a burst, they instantly relay its coordinates to a global network of ground-based and space-based telescopes, which swiftly pivot to stare at that single point in the sky. Astronomers then witness the afterglow's steady dimming, a direct observation of a shockwave losing energy as it expands into the void. What cosmic event could possibly trigger such an unfathomable release of power? These bursts are thought to be the birth cries of new black holes, either from the collapse of a massive, rapidly spinning star or from the cataclysmic merger of two ultra-dense neutron stars. The fading light of the afterglow is a rich source of forensic data, allowing scientists to decipher the physics of the explosion, the geometry of the jets, and even the composition and density of the material in the far-off galaxy where it occurred. The frequency of these universe-shaking events is not constant. In the earlier, more chaotic cosmos, when star formation was at its peak, gamma-ray bursts were far more common. Today, they are rarer, a testament to a calmer, more evolved universe. Each burst is more than just a fleeting flash. The material violently ejected from these explosions, enriched with heavy elements forged in the stellar collapse or neutron star merger, is scattered across intergalactic space. This contributes to the gradual chemical enrichment of the cosmos, a slower, more pervasive change that seeds future generations of stars and planets with the building blocks for complexity, and perhaps even for life itself. The very chemistry of the cosmos has been rewritten over time. The gas and dust drifting between the stars, the interstellar medium, did not always contain the ingredients for planets or life. In the beginning, it was a pristine sea of only the lightest elements, hydrogen and helium, with just a whisper of lithium. That was all the universe had to work with. But then the stars began their work. For billions of years, supernovae have acted as cosmic forges, and stellar winds have blown like cosmic breezes, carrying newly cooked elements out into the void. They have progressively enriched this raw material with heavier atoms, carbon, oxygen, iron, gold, everything that makes up our world and our bodies. We can read this history of cosmic pollution like a timeline in the stars themselves. The oldest stars in our galaxy, found in the halo, are metal poor, meaning they contain only tiny amounts of these heavy elements. They are the pristine relics of an earlier, simpler universe. In contrast, younger stars like our Sun, which formed much later, are metal-rich, having condensed from gas that had already been seeded with the ashes of countless generations of dead stars. This enrichment is not a uniform process. Look within a single galaxy and you will find a chemical gradient. The central regions where star formation and stellar death have been most frantic are more heavily enriched. The outer fringes remain more pristine, closer to the ancient composition of the universe. This chemical diversity means that the potential for building complex structures has grown over the eons. A cloud of gas today is not the same as a cloud of gas 10 billion years ago. It is now laced with carbon compounds and silicate dust, the very stuff needed to form rocky planets, oceans, and the complex molecules that are the precursors to life. The universe has, in a very real sense, become more interesting, more capable of complexity, because of this gradual chemical evolution. And this enriched material, this cosmic compost, is what eventually collapses to form not just new stars, but entire new planetary systems with a far greater diversity of worlds. The familiar shapes in our night sky are a beautiful illusion of permanence. Each star in a constellation is not a fixed point of light, but a distant sun on its own independent journey through the galaxy. This individual stellar movement, the slow drift across the celestial sphere, is what astronomers call proper motion. While these shifts are far too small for our eyes to perceive in a human lifetime, over tens of thousands of years they will completely redraw the star maps we know so well. The Big Dipper, that trusted guidepost, will slowly unravel. In 50,000 years, its iconic ladle shape will be stretched and distorted into a form our ancestors would not recognize. We are not left to merely imagine this future. Satellites like Gaia have given us a dynamic, three-dimensional movie of our galaxy, precisely tracking the velocities and directions of over 1 billion stars. This data reveals a cosmos in constant, swirling motion, with stars streaming along their vast orbital paths around the galactic center at different speeds and on different inclinations. The serene tapestry of the night sky is therefore a fleeting alignment, a single frame in a film that spans hundreds of millions of years. This grand stellar drift is a direct consequence of the galaxy's own evolution, a local echo of the immense gravitational dance that governs the entire Milky Way. That grand stellar drift is part of a much larger and more intricate dance, the slow, majestic spin of the entire galaxy. A spiral galaxy like our own Milky Way is not a solid pinwheel, but a swirling collection of billions of stars, each on its own independent orbit around the galactic center. This creates one of the most beautiful puzzles in all of astronomy, the winding problem of the spiral arms. If those graceful arms were simply fixed structures made of the same stars, the galaxy's rotation would tear them apart. The inner stars orbit much faster than the outer ones, so over a few 100 million years, the arms would wind up tighter and tighter, like strands of syrup in a stirred cup of coffee, until they completely vanished. Yet we observe spiral galaxies of all ages, their arms clearly defined. This paradox reveals a profound truth, that the spiral arms are not permanent features but shimmering patterns, like traffic jams in the flow of stars and gas. They are density waves, regions where the gravitational pull temporarily compresses material, slowing its passage. Think of a wave moving through a crowd in a stadium. The people stand up and sit down, but the wave itself travels around the arena. In a galaxy, stars and gas move in and out of these spiral density waves. As a cloud of gas enters the wave, it gets squeezed, triggering the birth of brilliant, short-lived blue stars that brilliantly outline the arm. Those massive stars then die out by the time they leave the other side, leaving the pattern clearly visible even though the constituent stars are constantly changing. We can study this dynamic process by creating detailed kinematic maps of nearby galaxies, tracking the subtle motions of stars and gas. These maps confirm that the pattern speed of the spiral arms is different from the orbital speed of the material, a delicate balance that prevents the winding catastrophe. This means the most iconic feature of a spiral galaxy is a transient, evolving phenomenon. The arms themselves can form, strengthen, and fade over cosmic time as the density wave propagates, reshaping the galaxy's appearance on timescales of hundreds of millions of years. This grand, rotating pattern does more than just create a beautiful image. It directly influences the environment for every star system within it, orchestrating the cycles of star birth and death on a galactic scale. Our planet itself is a spinning top in a slow, graceful wobble. Earth's rotational axis traces a wide circle in the celestial sphere over a cycle of 26,000 years, a grand celestial rhythm known as precession. This means the star we call the North Star is a temporary guide. Right now, Polaris marks our north, but in about 13,000 years, the brilliant star Vega will take its place before Polaris returns to its pole position thousands of years later. This gyroscopic motion is driven by the persistent gravitational tugs from the Sun and Moon on Earth's slightly bulging equator, a gentle but relentless force that changes our orientation in space. This shift is more than a celestial curiosity. It alters the timing of our seasons over immense timescales. The gradual change in which hemisphere is tilted toward the Sun at its closest point in Earth's orbit is one of the key drivers of our planet's ice age cycles, a rhythm we can read in the layered ice cores drilled from ancient glaciers. But Earth is not alone in this slow dance. The orbits of the planets themselves also precess, their elongated ellipses slowly rotating around the Sun. Mercury, the innermost planet, provides the most stunning example. Its orbit precesses due to the curvature of spacetime itself, a direct prediction of Einstein's theory of general relativity. The tiny extra shift in Mercury's orbit, a change we can measure with exquisite precision, was a key piece of evidence that confirmed our modern understanding of gravity. These precessional cycles, both of spin and orbit, are predictable and measurable. They demonstrate that even the most stable-seeming frameworks of our solar system are in a state of continuous, graceful evolution. This slow, rhythmic wobble is a constant background hum, a cyclical change layered atop a more fundamental and irreversible process that awaits many cosmic objects. Gravity's embrace writes a final chapter for every satellite. Look up at the moon, a familiar face that never turns away, forever hiding its far side from our view. This is not a coincidence of its birth, but the result of a slow, gravitational negotiation completed long ago. The moon is tidally locked, its rotation perfectly synced with its orbit around Earth, a state reached after billions of years of gravitational friction. Our planet's pull subtly distorted the moon's shape, creating a slight bulge, and the relentless tug on that bulge acted like a brake, slowing its spin until it matched its orbital journey. This same process is actively reshaping other worlds right now. Many of Jupiter's and Saturn's moons are caught in this cosmic slow dance, at various stages of becoming tidally locked. Their geology is often a direct result of this constant gravitational squeezing, the friction heating their interiors to create volcanoes and subsurface oceans. But this tidal tug-of-war does more than just synchronize spins. It can also steal energy from an orbit itself. Mars' moon Phobos presents a stark and dramatic example of this orbital decay. A small, lumpy world, Phobos is spiraling inward towards the red planet, drawing closer by about 6 feet every century. In tens of millions of years, its path will dip inside the Roche limit, the point where a planet's tidal forces are stronger than the gravity holding a moon together. When that happens, Phobos will be shredded, transformed from a moon into a brilliant, temporary ring of debris around Mars. We are not merely predicting this fate, we are measuring it. Astronomers use techniques like laser ranging, bouncing light off reflectors left on the moon, and precise timing of orbital cycles to detect these minuscule changes in distance and period. The data confirms a slow, relentless process that is continually reshaping planetary systems. This tidal reshaping is a universal architect. For a potentially habitable exoplanet orbiting a red dwarf star, tidal locking is often the default state, with one hemisphere in perpetual daylight and the other in endless night. This dramatically alters the climate and potential for life, and as an orbit decays, the gravitational energy lost does not simply vanish. It is dissipated as intense physical heat within the moon or planet, a friction that can melt rock and sustain global oceans under ice. This tidal heating is the engine behind the volcanic fury of Io and the hidden seas of Enceladus. It is a fundamental force that governs the long-term stability, geology, and ultimate fate of worlds, a quiet vibration that builds into a transformative fire. That same tidal friction which can tear a moon apart also possesses the power to bring a world to life. Far from the sun's warmth, a moon like Jupiter's Europa should be a frozen, inert ball of ice. Yet beneath its cracked, icy shell lies a global ocean containing more liquid water than all of Earth's seas combined. This ocean persists because of tidal heating, the relentless internal friction generated as Jupiter's immense gravity flexes and squeezes the moon's core. With every elliptical orbit, Europa is stretched and compressed, its interior kneaded like warm dough, generating enough heat to keep a vast sea from freezing solid. This is not a gentle warmth, it is a geological engine. We have seen the spectacular evidence of this process at work on Saturn's moon Enceladus, where towering geysers of water ice and organic molecules erupt from fractures in its south pole, painting the tiny moon's surface with fresh, bright ice. These plumes are a direct sample of a subsurface ocean, a cryovolcanic declaration that this world is alive with internal energy. The intensity of this heating is not a fixed value, It is a direct consequence of a moon's orbital dance. A more elongated, eccentric orbit creates stronger tidal flexing, while a circular path leads to a quieter, colder state. As the orbits of these moons slowly evolve over millions of years, pulled by the gravity of their sibling satellites, their internal furnaces can be stoked or dampened. A moon that is today a frozen wasteland could, in its past or future, have been a warm, watery world. We can actually measure this change from a distance. Spacecraft like the Galileo probe and the Cassini orbiter have mapped the surface temperatures and geological activity on these distant moons, providing direct evidence of their internal heat. This reveals a profound truth about the potential for life in the cosmos. A moon's habitability is not a permanent condition. It is a dynamic state, a fleeting window of opportunity that opens and closes in rhythm with the gravitational music of its planetary system. Having journeyed through these 20 transformations, from the accelerating expansion of the universe to the hidden oceans of icy moons, a single, overwhelming theme emerges. The cosmos is not a museum of static exhibits. It is a living, breathing, and ever-evolving entity. Every layer of reality, from the grandest galaxy to the smallest spinning asteroid, is caught in an endless dance of change. The universe we see tonight is just a single, fleeting frame in an epic movie spanning billions of years, a story that is still being written, and one we are only just beginning to read. Each of these 20 transformations is a single thread in a vast cosmic tapestry. The expansion of space does not simply push galaxies apart. It sets the stage for their eventual collisions by dictating the initial conditions of their dance. The violent death of a massive star in a supernova does more than create a brilliant flash. It seeds the surrounding gas clouds with the heavy elements necessary for rocky planets and life itself. The furious activity of a supermassive black hole, blazing as a quasar, eventually shuts down star formation in its own galaxy, a dramatic act of self-regulation. These are not isolated events, they are deeply interwoven cause and effect. The heating of intergalactic gas by countless galactic outbursts makes it harder for new galaxies to form, directly linking the energetic past to a quieter future. This reveals a cosmos governed by intricate feedback loops and grand cycles. A change in one realm ripples across the entire system, influencing conditions billions of years later. When we piece these connections together, we stop seeing a universe of separate objects and start to perceive a single, complex, evolving entity. It is a grand, continuous narrative written across billions of years, where the fiery birth of the first stars directly shaped the chemical makeup of the cloud that would one day form our Sun and Earth. This holistic view transforms our understanding. We are not just looking at distant, static points of light. We are witnessing a story in which the past actively forges the present and scripts the future. Recognizing this profound interconnectedness deepens our appreciation for the dynamic, living reality we are a part of, and it brings us to a final, inevitable question about our own place within this endless transformation. This grand, interconnected tapestry of change finds its ultimate meaning in us. We have journeyed through 20 unexpected ways the universe transforms, from the accelerating expansion of space to the hidden oceans churning inside distant moons. Each one stands as a testament to a cosmos in perpetual motion, a reality far more dynamic and alive than the still and silent painting of our night sky suggests. These are not abstract theories confined to chalkboards, but observable, measurable transformations. We watch galaxies collide, we track the fading glow of stellar explosions, and we measure the slow wobble of our own planet's axis. This ongoing, relentless evolution shatters the ancient notion of a static and unchanging heaven. placing us instead within a living, breathing cosmos that has a deep history and an unfolding future. We are not separate from this story. The astronomer Carl Sagan captured this profound connection when he said, "The cosmos is within us, we are made of star stuff." The iron in your blood was forged in a stellar furnace that died before the sun was born. The calcium in your bones was scattered across space by a supernova's violent breath. We are not just observers of these cosmic changes, we are products of them, the universe becoming conscious of itself. Let this